Problem 3 on quiz number 2 was something that tripped up quite a few of you. So the problem is we have CaH18, which is octane, and it's burning, or it's combining with oxygen, essentially combustion burning, and it makes carbon dioxide and water. So the question I gave you was, if we have 3.55 liters of octane, and we combine it with 9.89 kilograms of oxygen, how much carbon dioxide in kilograms do we produce? And I told you the caveat that this reaction proceeds with 85.5% yield. It should be second nature to you at this point, hopefully you've done enough homework problems, that, okay, this is a stoichiometry problem. But I've given you an amount for each of the reactants, so that makes it a limiting reagent problem. If I told you that we had excess oxygen, then you would start with this value and off you go. Or if I told you we had excess CaH18, you would start with that value and off you go. But for a limiting reagent problem, we're going to have to do, in this case, 2 calculations. So I'm going to work through that right now. 3.55 liters of octane. Well, liters is not moles, obviously, but that's a good place to start. And it's a little cumbersome to write CaH18 in there every time, but it is worth it to keep track of the units. I'm going to give myself some space. And we want, make sure this is visible, kilograms of our octane for our final answer. Liters is a volume. Well, I gave you the density of octane as being 0.0703 grams per milliliter. But to get to that, we need to convert from liters to milliliter. So 1 liter of octane is 1,000 milliliters. Liters cancel. Now I'm in milliliters. Now we can use the density value that I gave you. 0.703 grams of octane per milliliter of octane. Some of you didn't recognize that you had to convert using the density relationship. So you just kind of stop. With dimensional analysis, it doesn't matter that this is a stoichiometry problem, but I have to start it by doing a density problem, because it's all about just converting units. So look what I've done. I've gone from liters to milliliters to grams of octane. Well, grams of octane is very close to what I need. Now I need moles of octane. If you notice, I gave you the molar masses, so that should have sped things up quite a bit. 114.26 grams of octane. I'm going to put the octane underneath just to save some space so I don't run out of room on the board. Gives me 1 mole. Of octane. Grams of octane cancel. I'm in moles of octane. Now, finally, I can use my balanced chemical equation. For every 2 moles of octane, I produce 16 moles of CO2. Remember, oh, geez. Sorry about that. We're trying to determine the kilograms of carbon dioxide, not octane. So that was my mistake. We're moving forward with our balanced chemical equation. 2 moles of octane equivalent to 16 moles of CO2. Moles of octane cancel. Now we have moles of carbon dioxide. We want kilograms, so we're very, very close. So now what we have to do is, well, 1 mole of CO2 is 44.01 grams of CO2. Okay. Moles of CO2 cancel. I'm in grams of CO2. I want kilograms. So 1,000 grams for every 1 kilogram, again, of CO2. Grams of CO2, kilograms. I would be done except for one thing. I gave you a percent yield. This reaction is 85.5% yield. So the way we can represent that, for every 100 kilograms of CO2 I produce, I isolate 85.5 kilograms. Sorry, I'm going from one board to another. So for every 100 kilograms of CO2 I produce in theory, I isolate 85.5 kilograms of CO2. Again, this is a unit where the values of CO2 cancel because I'm putting in a percentage. So now I have included my percentage. I'm in the unit of kilogram. When I do this, after all is said and done, I get 6.57 kilograms of CO2. But I'm not done. That was for the octane, the C8H18. I have to do a second calculation for the oxygen because I don't know which one is the limiting reagent. So we set this up the same way. This one will be hopefully a little easier since we don't have to deal with density. So we have 9.89 kilograms of oxygen. Put that in there. And we want kilograms of CO2, just as we did in the previous problem. All right, well, kilograms of O2. I'm going to have to convert that into moles, but to get to moles, I have to convert to grams. The only dimensional analysis unit conversion I expect you to memorize are the metric ones. Kilograms to grams, milliliters to liters, centimeters, and so forth. O2. Kilograms of oxygen cancel. Now I'm in grams. 32 grams of oxygen, of O2 I should say. Put that down here so it doesn't look like that. Is equivalent to 1 mole of O2. I didn't put the molar mass of oxygen on here because I want you guys to have to calculate that. It's not very difficult. Again, 2 times 16. Grams of oxygen cancel. Grams. So now we're in moles of oxygen. 25 moles of oxygen creates 16 moles of CO2. This should start to look a little bit familiar once we get past this step. 16 moles, oops, excuse me. That. All right, so moles of oxygen cancel. Now I'm in moles of CO2. And you can see we're going to actually finish the problem exactly the same way. So 16 moles of CO2, but I want kilograms of CO2. 1 mole CO2, 44.01 grams CO2. Okay, moles to grams, 1,000 grams CO2 to 1 kilogram of CO2. Grams cancel. And I have to include the percent yield, just as I did before. So 100 kilograms of CO2 are produced in theory, but we only isolate 85.5 kilograms CO2. Sloppy. Mathematically, if you just multiply by 0.855, it's the same thing. But I like to set it up formally. Kilograms cancel, or you can just cancel those two, it doesn't matter. And we still end up with kilograms of CO2. So now, we just plug this into our calculator, and I got 7.44 kilograms. Well, in the previous problem, we've got 6.57 kilograms of CO2. This value is larger. So what that means is octane is the limiting reagent, and the maximum amount of carbon dioxide that we can produce is 6.57 kilograms. Now you might be saying, well, wait a minute, why did I have to do the second calculation? Well, if this number would have been less than 6.57, then it would be the correct one. So you don't flip a coin or just assume it's the first equation. You have to work through both of them, or 3 of them if there were 3 reactants, or 4 of them if there were 4 reactants. So don't take a shortcut and just do the first one and say, oh, I'm done, because in this case, you would have lucked out. If I would have made this value the limiting reagent, then you would have gotten it wrong.